Why the James Webb Telescope's new discovery has astronomers so alarmed. For nearly a century, scientists have been trying to answer one seemingly simple question: what is the exact value of the Hubble constant? This number, though it may appear straightforward, actually determines the rate at which the universe is expanding. Its accuracy doesn't just affect our ability to measure the size of the cosmos, it also shapes how we predict the universe's future evolution. But now, the latest data from the James Webb Telescope has completely shattered our understanding of this critical number. This isn't just a scientific hiccup, it's a fundamental challenge to our entire cosmic worldview. And to unravel this mystery, we have to start by re-examining the Hubble constant itself. The Hubble constant was first proposed 100 years ago, when astronomer Edwin Hubble made an initial estimate based on his observations, 500 kilometers per second per megaparsec, that meant the universe was expanding at a speed so fast it was almost unimaginable. Picture this. It's like decorating a cake with whipped cream, only to watch in shock as the cream suddenly spreads out and engulfs an entire city. That mind-boggling expansion rate made scientists skeptical, and they decided to double-check Hubble's findings. To do this, they turned to the cosmic microwave background radiation, the faint afterglow of the Big Bang, formed about 400,000 years later. This radiation shows cooler patches in space, areas where the first stars and galaxies began forming under gravity's pull. By comparing these ancient microwave images with what we see in the universe today, astronomers concluded that the cosmos was actually expanding much slower than Hubble's estimate. The new figure, 6 to 7 kilometers per second per megaparsec, just 1/7 of Hubble's original calculation. Now, instead of the whipped cream covering a city, it would only fill a kitchen. But instead of breathing a sigh of relief, scientists decided to test this result another way. This time, they measured how fast galaxies are moving away from us using something called standard candles, celestial objects with known brightness, like Cepheid variable stars and red giants. Think of it like judging a car's distance by how bright its headlights appear. Using this method, the Hubble constant came out to 73 kilometers per second per megaparsec, but here's the problem. That's more than 10% higher than the microwave background measurement. This discrepancy threw scientists into chaos. If two of the most reliable methods give different answers, it means something is deeply wrong with our foundational theories. Either we've misunderstood the universe's evolution, or decades of data and research might need to be thrown out entirely. Faced with this dilemma, some scientists thought it might be easier to admit that the standard candle method was flawed rather than rework the Hubble constant. It's like rewiring an old house, annoying, but still better than tearing it down and rebuilding. But then, the James Webb Telescope dropped a bombshell. Astronomers expected the most distant galaxies to be primitive and simple, with barely any structure. Yet, in Webb's first images, they found ancient galaxies that were bizarrely complex and far more advanced than predicted. Even stranger, in just 1 year, Webb found 4 times as many of these galaxies as had ever been seen before in the entire history of astronomy, and the surprises didn't stop there. In a distant, flame galaxy, Webb unexpectedly captured an image of a Cepheid variable star. If Hubble's earlier calculations weren't wrong, this was the moment of truth. Shockingly, Webb's new data matched previous observations almost perfectly, meaning the standard candle method still held up. So where's the problem? It turns out the issue lies in our understanding of the cosmic microwave background. This discovery doesn't just redefine the universe's expansion rate, it shakes the very foundation of cosmic evolution theory. We always assumed the universe expanded at a steady pace, but now we are forced to reconsider. Maybe the real issue isn't that our science is wrong, but that we've overlooked a crucial fact: the universe is far stranger than we ever imagined, and its structure defies our current frameworks. Could we explain these discrepancies? One possibility is that the universe isn't finite, as we've assumed, but infinite. If that's true, then any attempt to define its size or shape might be doomed from the start. But why can't we just accept that? Because an infinite universe comes with a terrifying consequence: its structure could eventually tear everything apart. So what makes an infinite universe so dangerous? Back in 1922, mathematician Alexander Friedmann proposed a model of an infinite cosmos, but it was dismissed as pure mathematical fantasy. Yet his ideas laid the groundwork for future breakthroughs. To test whether the universe is finite, scientists measured its curvature. A result of 0 would mean infinity, Anything else would imply a finite shape. The answer was unsettling. The universe's curvature was nearly zero, accurate to 90%. That suggests an endless, flat plane. Why is that dangerous? Because if the universe is truly infinite, its accelerating expansion could reach a point where even the original Hubble constant would seem tiny. Galaxies would fly apart, the Milky Way would dissolve, and eventually, even our solar system would break apart. This scenario, known as the Big Rip, predicts that all matter will be shredded into a thin particle soup, leading to total cosmic collapse. Marcello Visconti's calculations suggest Earth could face this fate in around 22 billion years. That may seem like plenty of time, but for future civilizations, it could arrive without warning, no matter where they are in the universe. Yet in recent years, more scientists have begun questioning both the Big Rip and the idea of an infinite universe. Thanks to the Planck Space Telescope's ultra-detailed map of the cosmic microwave background, we now have even more precise curvature data. The latest readings show the universe's curvature is almost zero, with an error margin of just 0.4%, far tighter than the previous 10%. But that doesn't mean we can take this result at face value. Astronomers analyzing the data have raised a new concern. If the curvature falls within this tiny error margin, the actual universe might be much larger than what we can observe. Right now, we can see about 93 billion light-years across, but Planck's data suggests the real universe is at least 250 times bigger. That might sound unbelievable, but history has taught us this lesson before. Early humans struggled to accept Earth was round because, from the ground, its curvature was invisible. Similarly, we might need new ways to measure the universe's true shape. According to Planck's latest analysis, the universe's curvature is far smaller than expected, almost undetectable, similar to Earth's. That means the cosmos might not be curved or finite at all, but nearly flat. Yet if the curvature really is that minuscule, the universe must still have some final shape, one that will decide its ultimate fate. Scientists have proposed several possible scenarios, each more grim than the last. The universe's geometry, in the most literal sense, could be deadly, meaning its structure might doom all future existence to an irreversible catastrophe. To understand this, we'd need to measure the density and curvature of deep space, but that's no easy task. The universe isn't made of ordinary matter and energy, it's dominated by dark matter and dark energy, whose distribution and behavior remain a mystery. Imagine pulling a tablecloth unevenly, eventually, it wrinkles. The universe might be undergoing similar distortions, especially if its density fluctuates. These ripples could warp the fabric of space itself. If the curvature is positive, within Planck's tiny error margin, our universe might not be flat, but a vast four-dimensional hypersphere. Picture a sphere, but with an extra dimension, a mind-bending concept for our 3D brains. Just as a circle differs from a sphere, a hypersphere takes our understanding of space to a whole new level. In 2019, cosmologist Alessandro Melchiori studied this hyperspherical universe idea. If correct, the Big Rip might be less likely. But the story doesn't end there. Scientists must also grapple with dark matter and dark energy's role. These mysterious forces drove the universe's rapid expansion after the Big Bang, and even now, they are accelerating it exponentially. This acceleration has smoothed out the universe so much that we can't accurately measure its curvature. But the real issue might not be expansion, it could be dark matter itself changing over time. In 2017, astronomer Gongbo Zhao and his team proposed a startling idea: dark matter might thin out, eventually reversing its push on expansion and triggering a collapse. This Big Crunch scenario would see the universe shrink back to a single point, with gravity growing so strong that stars collide, and even humans could be crushed into the ground. In the most extreme case, the Big Crunch could trigger a new Big Bang, wiping out everything. Yet Planck's data leaves us with another puzzle. Its curvature measurement, with that 0.4% error, could also be negative, meaning the universe might be saddle-shaped. Unlike a hypersphere, this shape would be a finite, four-dimensional fragment. So what's the universe's true form? Make sure to hit that subscribe button, give this video a thumbs up, and share it with your friends and family. Thanks a bunch.